But this is a single circuit, and this is the ideal. I mean, just so you get the hang of those, the V equals IR is what applies to here. There are a lot of times, though, that in your house you don't just have one little unit that's, you know, a radio or something like that that's plugged in. Sometimes you'll put a whole series of things plugged in across your house. And that might be shown a little interesting because there's several ways you can hook up several different instruments. Or think about Christmas lights if you put those out, and there'll be all these lights in a row. Or it's a whole series of, you know, you're sitting at your technology desk, you're working on your computer, and you've got, you know, your iPod and the next, you know, all your devices are all plugged in. So here's the electric outlet. There's your source of electricity. And let's put that back at 120 volts, for instance. And let's just put a bunch of resistors. So here's your radio. Here's your iPod. God, what year am I in? This is your iPhone or your Android or whatever. Let's say on its way back, you're going to plug one more thing in. It's just the light that you're working on, or maybe the computer or something like that. Okay, all of those, the electricity is going to flow into one and out the other side. That same electricity is going to go into here and come out the other side. So you start off high on this hill. That's what the electron voltage is you put the electrons up here, and then as they go through each of these instruments, they get lowered in energy as they go through. So let's give the radio a small, because that doesn't take a lot of electricity. Let's call that maybe a 4 ohm resistor. iPhone is also super small. Let's make that about 1 ohm resistor. Then the light, let's say that takes a little bit more, and that's going to be a 5 ohm resistor. What is the total current going through here? Okay, when a bunch of these are hooked up in a row. Well, the key is to think, gosh, can I reduce these down to 1 so that I can just use the same law that I was up here? What, fortunately for us, is that when a bunch of resistors are hooked up in a row, this is called a series circuit, so that the electrons go through in a series, goes through one each. That, for instance, the resistance of the whole circuit is just the total of adding these up. It's super straightforward. So if it loses whatever we find out the current is through here, it's going to lose a little bit more through there and a little bit more through there. It's going to be as if these were all one resistor. That equals the resistance of 1 plus the resistance of 2 plus the resistance of 3, the third thing. So your radio, your iPhone, and your light. Well, that's pretty straightforward. 4 plus 1 plus 5, that's just 10. Okay, is what the total resistance. And what you can do there is once you've got a replacement or an equivalent resistor for the total circuit, is now we can do the equation V equals IR to find out what the current is. Okay, so we're going to find that total. And we got 120 volts. The current is what we're looking for. This is 10 ohms. And so the current, after I divide both sides by 10, is going to be just 12 amps. So all three of those together are going to run at 12 amps. All right. So that is a series circuit. Anytime all of the electronics go, you know, in a row, that the electricity has to go out. Now, if one of these shorts out, for instance, that would stop, or, you know, something happens where it breaks this circuit somewhere, then none of them will work because the electricity has to pass through these, all of those. So that's the current, and that's the bummer about using a series circuit. Okay, because once it breaks, then nothing can work. Okay, we're going to talk about another circuit here in a second.